Welcome to my channel. Today, let us understand the basics of the functioning of vaporizers. We all know anesthesiologists use inhalational anesthetics for induction and maintenance of anesthesia. Every anesthesiologist should understand the basic physical principles and the way they influence the design of the vaporizer, as this will help the anesthesiologist to select the vaporizer well suited for his or her practice and to use them economically, safely, and to maintain them in optimum working condition. Inhalational anesthetic agents need to be delivered to the lungs for them to work. Of course, one cannot simply pour them into the lungs. A much more acceptable way is to convert the liquid inhalational agent into a form that can be delivered by the inhalational route to the patient. The most convenient way is to deliver the vapor form of the liquid inhalational agent. A device which converts liquid to vapor is called a vaporizer. So, vaporizer is defined as an instrument designed to facilitate the change of a liquid anesthetic into its vapor and add a controlled amount of this vapor to the flow of gases going to the patient. Now, as you can see, there are two components in this definition. One is converting the liquid inhalational anesthetic into its vapor. But can you give this entire vapor directly to the patient? No. So the other component of a vaporizer is to add a controlled amount of this vapor into the flow of gases going to the patient. And that is the reason why we need to understand exactly how the vaporizers work, because as end users, as anesthesiologists, control the amount of vapor going into the patient's lungs. Now, before going on to discussing vaporizers, we need to first understand some basic crucial concepts. First, let us understand what is the difference between gas and vapor. Are they the same? In simple terms, a gas is a substance that naturally exists in a gaseous state at room temperature, while a vapor is the gaseous state of a substance that is usually a liquid or solid at room temperature. Essentially, vapor is a gas that was once a liquid or solid, and it can condense back into its original state. If you take a gas and compress it really hard, the particles that compose it are brought close to each other. As you keep compressing, the particles will at some point coalesce and convert the gas into a liquid. So, if a vapor is compressed, by increasing the ambient pressure, it will return to the liquid state. However, a temperature exists above which it will not become a liquid, however much it is compressed. This temperature is called its critical temperature, and above this, the substance exists as a gas. So, critical temperature is therefore defined as the temperature above which a substance cannot be liquefied, irrespective of the pressure applied. So, strictly speaking, a gas is a substance above its critical temperature. Let us take isoflurane as an example. The critical temperature of isoflurane is about 200 degrees Celsius. Therefore, at room temperature, that is 21 degrees Celsius, the gaseous phase of isoflurane would be called isoflurane vapor. This brings us to another basic concept, vaporization. Now, what is vaporization? Vaporization of an element or compound is a phase transition from the liquid phase to vapor. There are two types of vaporization, evaporation and boiling. Evaporation is a surface phenomenon, while boiling is a bulk phenomenon. In a liquid, the molecules at the surface of water are loosely attached to each other as compared to the molecules beneath the surface. Evaporation is an endothermic process. When a liquid evaporates, it requires energy in the form of heat to break the intermolecular bonds and transition into a gas. This energy is drawn from the liquid itself, causing the temperature to drop. Sometimes, collision of air or wind can also have the same effect. The difference in temperature between the liquid and its surroundings creates a temperature gradient. Heat naturally flows from areas of higher temperature to areas of lower temperature. In this case, heat flows from the warmer surroundings into the cooler liquid. As the liquid cools, the temperature gradient between the liquid and its surroundings increases, leading to a greater flow of heat into the liquid. Eventually, the rate of heat flowing into the liquid from the surroundings will match the rate of heat being lost by the liquid through vaporization. At this point, the liquid's temperature will stabilize and the process will reach a state of equilibrium. At this point, the temperature ceases to drop. Thus, if a glass of water or any liquid is left exposed to the atmosphere, the water will eventually disappear. We say that it has evaporated. The water has changed its physical state from a liquid to a gas. The higher the temperature of the liquid, the quicker it evaporates because the higher energy of the molecules means more can break free from the liquid. So on a hot day, the glass of water evaporates more quickly than on a cold day. So this kind of vaporization of a liquid that happens using its own heat that it has taken from the surroundings is called evaporation. The heat energy required for this process is termed the latent heat of vaporization. The amount of heat that is needed to convert the unit mass of liquid substance into a gaseous phase at constant temperature conditions is known as latent heat of vaporization. Boiling means rapid vaporization of any liquid by application of heat. In a liquid, the molecules have stronger intermolecular forces that hold them together and prevent them from escaping the liquid surface. When heat is applied, these molecules begin to vibrate, and as more and more heat is applied, a point is reached at which this energy is enough for the intermolecular forces to be broken, and molecules are released into the gaseous state. This is called boiling, and the temperature at which this happens is called the boiling point of the liquid. So, for a given ambient temperature, the closer a liquid is to its boiling point, the quicker it will turn into a vapor. This is because the kinetic energy of the molecules increases as they approach boiling point. Therefore, at room temperature, that is 20 degrees Celsius, a jar of ether whose boiling point is 35 degrees Celsius will turn to vapor quicker than water whose boiling point is 100 degrees Celsius. Previously, we discussed how in a liquid that is undergoing vaporization, a state of equilibrium is achieved. The vapor pressure of a liquid is the pressure exerted by the vapor above the liquid surface when the liquid and the vapor are in equilibrium. Now let us try to understand what are the factors that affect the vapor pressure and thus the formation of vapors. So here in the first figure, the liquid and the vapor are in equilibrium. In the second figure, we can see that the application of heat causes the equilibrium to shift so that more molecules enter the vapor phase as shown by the increased density of dots above the liquid. Now in the third figure, we can see that lowering the temperature causes a shift towards the liquid phase and a decrease in the vapor pressure. And finally, in the fourth figure, we see that passing a carrier gas over the liquid shifts the equilibrium towards the vapor phase by recruiting more molecules from the liquid. Since the heat that is used comes from the latent heat within the liquid, the temperature of the liquid drops. As you can guess by now, we are slowly trying to understand the factors that influence vaporization of a liquid anesthetic and how we can control it by using a vaporizer. Now, let us imagine what happens if we put the water or liquid in a jar with a sealed lid. The process of evaporation still occurs, but molecules not only leave the liquid but also re-enter the liquid as they cannot escape from the jar. Eventually, a state of equilibrium is reached where the number of molecules leaving the surface of the liquid is the same as the number re-entering the liquid. Because the molecules in gaseous form have kinetic energy, they bounce off the walls of the container and exert a pressure that can be measured. This pressure is called the saturated vapor pressure, and like all pressures, it is measured in kilopascals. Same happens with the liquid in a vaporizer. Evaporation is the phenomenon by which molecules in the liquid phase with high kinetic energy escape from the surface of a liquid to enter the gaseous phase. Inside the vaporizer, molecules will enter the gas phase until the rate of vaporized molecules equals the rate of molecules returning to the liquid phase. This dynamic equilibrium is known as saturation. The pressure exerted by this gas is known as saturated vapor pressure. So, saturated vapor pressure is defined as the pressure exerted by the vapor of a substance's pure liquid or solid phase when at a given temperature it is in equilibrium with a plane surface of that substance. The saturated vapor pressure of a liquid is independent of the ambient pressure but increases with increasing temperature. So if we continue to heat a liquid at a certain temperature, the liquid molecules can enter their vapor phase within the liquid, creating bubbles of saturated vapor that rise to the surface and break free. Below this temperature, any formation of a bubble would be instantly crushed by the greater atmospheric pressure. Thus, at a certain temperature, the liquid eventually starts to boil and the SVP equals the ambient pressure, which is usually 101 kilopascals. This temperature is called the boiling point. Therefore, the boiling point of a liquid can be defined as the temperature at which its saturated vapor pressure equals the atmospheric or ambient pressure. So, why is saturated vapor pressure so important to anesthetists? The answer is that it allows us to generate known concentrations of vapor. Higher SVP means more anesthetic can be delivered, potentially leading to faster induction of anesthesia. Understanding SVP is essential for proper vaporizer selection and adjustment to achieve the desired anesthetic depth. This table shows the saturated vapor pressures of some commonly used inhalational anesthetics at 20 degrees Celsius. Now, the Dalton's law of partial pressures states that the total pressure of a gas mixture in a container is the sum of the partial pressures of the constituent gases. The partial pressure exerted by the vapor of a liquid agent depends only on the temperature of that agent and is unaffected by the total pressure above the liquid. The highest partial pressure that can be exerted by a gas at a given temperature is its vapor pressure. Now you will ask, what should we do with all of this information? The implication of this is that if we generate a saturated vapor of a liquid in air and deliver the mixture at atmospheric pressure, we can derive the volume percentage occupied by the vapor in a gas mixture, that is, its concentration. For example, if we consider our jar of water, the saturated vapor pressure of water at 20 degrees Celsius is 6.2 kilopascals. If atmospheric pressure is 100 kilopascals, the volume percent or concentration of the vapor is calculated as concentration of water vapor is equal to saturated vapor pressure divided by the atmospheric pressure, that is 6.2 divided by 100, which is 6.2%. This brings us to the next concept of gas concentration. So two methods are commonly used to express the concentration of a gas or vapor. One is partial pressure and one is volume percent. Partial pressure refers to the pressure that a specific gas would exert if it occupied the entire volume of a mixture at the same temperature, and it is the contribution of each individual gas to the total pressure of the gas mixture. Volume percent expresses the relative volume percent is the number of units of volume of a gas in relation to a total of 100 units of volume for the total gas mixture, and it expresses the relative ratio of gas molecules in a mixture, whereas partial pressure expresses an absolute value. Partial pressure divided by the total pressure is equal to volume percent. Although gas and vapor concentrations delivered by a vaporizer are usually expressed in volumes percent, patient uptake and anesthetic depth are directly related to the partial pressure. While a given partial pressure represents the same anesthetic potency under various barometric pressures, this is not the case with volumes percent. When we talk about anesthetic potency and patient uptake of a gas, we need to understand the concept of minimum alveolar concentration or MAC. The minimum alveolar concentration or MAC of a potent inhaled anesthetic agent is the concentration that produces immobility in 50% of patients who undergo a standard surgical stimulus. Used as a measure of anesthetic potency or depth, MAC is commonly expressed as volumes percent of alveolar end tidal gas at 1 atmospheric pressure at sea level, that is 760 mm of mercury. This table shows how MAC expressed in familiar volumes percent can be expressed as a partial pressure in millimeters of mercury. Anesthesiologists should learn to think of MAC in terms of partial pressure rather than in terms of volume percent, because the partial pressure or tension of the anesthetic in the central nervous system is responsible for the depth of anesthesia. This concept has been advocated by Fink, who proposed the term minimum alveolar pressure or MAP and by James and White, who suggested minimum alveolar partial pressure or MAPP. Now, as we have seen earlier, vapor pressure may vary depending on the factors affecting evaporation. So temperature of the liquid, surface area of the liquid, and rate of removal of vapor molecules from the liquid surface. At a given temperature, each agent will have a known saturated vapor pressure, as we have already seen in this table. If the gas leaves the vaporizing chamber containing agent at its SVP, then a fixed concentration of agent is delivered into the fresh gas flow. Now, let us take an example. At 20 degrees Celsius, the concentration of gas in a sevoflurane vaporizing chamber, assuming that it is saturated, will be, using the formula saturated vapor pressure divided by atmospheric pressure, comes to 21%. So, it would be possible to create sevoflurane vapor at a concentration of 21%, which is far greater than that needed for anesthesia and potentially dangerous. How much do we actually need for clinical use? Around 2%. So how to overcome this? To overcome this, modern vaporizers produce a saturated vapor and then mix this with a known volume of a carrier gas, usually oxygen, and either air or nitrous oxide to produce a known lower concentration of vapor using the principle above. Basically, we dilute the anesthetic vapor with the fresh gas. Now, how much vapor does a liquid anesthetic yield? Can we calculate it? The formula is given by vapor output of 1 ml of liquid agent is equal to 22,400 multiplied by density divided by molecular weight. So as we can see in this table, we have the vapor output calculated for various liquid anesthetic agents. Now, 1 milliliter of anesthetic liquid is able to produce up to 210 ml of anesthetic gas, though this varies between drugs. So the formula is the milliliters of liquid anesthetic per hour is given by 3 multiplied by the dial concentration multiplied by the fresh gas flow in liters per minute. Now this 3 becomes 3.3 if it is sevoflurane or 2.85 if it is desflurane. So how many milliliters of sevoflurane would be consumed if providing 2.5% volume by volume percent and a fresh gas flow of 3 liters? So ml of sevoflurane is equal to 3.3 multiplied by 2.5% into 3 liters per minute. That is 24.7 ml per hour of sevoflurane consumption. This is how we can calculate the consumption of the liquid anesthetic agent. Let us summarize what we have learned so far. So basically, till now we have understood a few basic things. Number one, we need to convert inhalational anesthetic agent into its vapors to use it clinically as a inhalational anesthetic. Second, supplying heat can hasten the process of vaporization. Third, passing a carrier gas over a vapor can recruit more number of molecules into the gaseous phase. Fourth, inhalational anesthetic has to be supplied along the flow of carrier gas. And 5, we need to calculate what percent of inhalational is going to the patient out of the total flow of gases for accurate delivery of inhalational anesthetic vapors. Before we try to understand how vaporizers work, we need to understand two more basic concepts. First is the specific heat. A substance's specific heat is the quantity of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius. The higher the specific heat, the more heat that is required to raise the temperature of a given quantity of that substance. Specific heat is important when considering the amount of heat that must be supplied to a liquid anesthetic to maintain a stable temperature when heat is lost during vaporization. Specific heat is also important for choosing the material to construct a vaporizer. Temperature changes more gradually for materials with a high specific heat than for those with a low specific heat. This table that depicts the properties of the common liquid inhalational anesthetic agents also shows the specific heat of each of them. Another consideration in choosing material from which to construct a vaporizer is thermal conductivity. Thermal conductivity is a measure of the speed with which heat flows through a substance. The higher the thermal conductivity, the better the substance conducts heat. So, in this video, we have seen the basics of vaporizers. We have discussed the properties of vapors and gas, concepts of critical temperature, vaporization, which includes evaporation and boiling, the concept of latent heat of vaporization and vapor pressure, the saturated vapor pressure and its importance to us as anesthetists, Dalton's law of partial pressures, various methods of calculating gas concentration, namely partial pressure and volume percent, and significance of each one of them, how to calculate the vapor output from a liquid anesthetic, and the concepts of specific heat and thermal conductivity. In my next video, we will see in detail the classification of vaporizers and learn how exactly various vaporizers work. I hope you have now understood the basics so that when you watch the next video, your concepts regarding the construction and functioning of vaporizers will be clear. Please like, subscribe and share my video with your colleagues and stay tuned for part 2 of Basics of Vaporizers. Thank you.